Hello, discrete math fans. We're now going to talk about division and the quotient remainder theorem and a proof technique called division into cases. But first, let's talk about division. If we take 25 and divide by 7, we'll get a quotient of 3 and a remainder of 4. What we mean by this is if we take 25 and divide by 7, we get 3 plus a remainder of 4. So that's 25 over 7 equals 3 plus 4/7. All right, another way we can think about this is that if we have 25 objects and we group them into groups of 7, we'll have 3 groups of 7, but then there'll be 4 left over. Here's a picture. There's 25 x's here. I've grouped them into 3 groups of 7 each, and then there's 4 left over. Finally, another way of thinking about it is that 25 can be written as 7 times 3 plus 4. So here we can say that we're thinking about 3 as being a quotient and 4 as a remainder. Now it's important that the leftover amount, in this case 4, is to be smaller than the size of the groups, in this case 7. Because if there were 7 or more in the remainder group, we could actually create another group of 7. So this whole concept of division in integers is stated in the quotient remainder theorem. So the theorem says that given any integer n and a positive integer d, there exist unique integers q and r such that n is equal to d times q plus r. And then the remainder that we get has to be a non-negative integer, but it has to be smaller than d. It has to be smaller than the divisor. Now we're going to give a complete proof of this theorem later in the class. Right now we want to just focus on using the theorem. Let's show a picture that will illustrate the quotient remainder theorem. Now this picture is only going to be good for when n is bigger than 0. We're going to have a different picture when n is negative. So the picture looks like this, that we find n on the number line, and then we keep adding multiples of d until we reach a point that if we add any more multiples of d, we'll go beyond n. So this gap in here between n and q times d, that's the remainder. So here the remainder has to be smaller than d, which d is the gap between these guys here. If we went a little bit farther, we would have q plus 1 times d, and that's going to be bigger than n. Now when n is less than 0, the picture is actually going to be different. Since n is equal to dq plus r, and r has to be non-negative, then what we have to do is we have to multiply d by a negative number q to get something that's less than n. Then we have to add a non-negative integer r to come back up to n. All right, so here's the picture. So here we're taking multiples of d until we get to the point where we reach q times d, which is actually less than n. If we don't go far enough, then we'll be at this point here, will still be bigger than n. And again, the gap that's between q times d and n is actually going to be the remainder. Now you might say, wait a minute, is this wrong here? How is that q plus 1 times d? Remember that d is a positive integer, so q plus 1 times d is actually the thing that goes above q times d. So this really is correct here. Okay, that's all for now.